Hi students, in the previous section we have studied few conservation laws to symmetry principles and to the invariance of the basic interactions under certain operations, and it was repeated. Okay, in this section we are going to introduce three more conservation laws. Okay, but in this time we are doing it in the reverse order. Okay, let us consider an interaction A interacting with B, and we will get C and D. Okay, using our Feynman diagram we can represent it as like this way. Okay, this is your A and this is your B, and you are getting C and D. Sorry, C and D. Actually, we have seen that various conservation laws stem from the fact that this reaction could take place in exactly the same manner at any point in space at another time, or with the original particle moving in other direction. Okay, or in other words, transforming the reaction in time or in space will not lead to some impossible events which would cause us to raise some problems. Okay, physicists concluded that three basic operations exist, named the time reversal operation, charge conjugation operation, and parity operation. Okay, that also need to be conserved. Okay, and we are going to study one by one. So first we will take the time reversal operation. Okay, so here the time reversal operation, this is our original interaction, that is A interacting with B, and you are getting C and D. Now after that you are applying your time reversal operation. Once you do the time reversal operation, then what will happen, all the reactions will take place in the reverse order, that is C interacting with D, and you will get A and B. Okay, so this it is conserved, this process is conserved in strong and electromagnetic interaction, and it is almost always conserved in weak interaction. Okay, or you can say the original reaction is invariant with respect to the operation of time reversal operation. Okay, next one is charge conjugation, or C. Sometimes in order to represent it as an operator, so we keep a cap, C cap. So what will happen if you apply your charge conjugation operator on a particle state? Okay, this is represented by our Dirac notation. Okay, the state is represented like this, you already studied. If you apply this charge conjugation operation on a particle state, then your output will be a antiparticle state. Okay, or this will just make the antiparticle by the charge conjugation operation. Or you can you will get it if you apply one more here, like another state, then you will get C square is equal to I, and the eigenvalue of C square is equal to 1, and the eigenvalue of C is plus or minus 1, or you can write the operator C acting on the particle state, that will give you plus or minus the particle state. Okay, just comparing these two. Okay, that you can do easily. And from equation 1 and 2, what you are getting, the antiparticle state is equal to plus or minus particle state. Okay, and using our Feynman diagram, you can see A interacting with B will give you C and D. This was your original interaction or original reaction, and now you applied your charge conjugation operation, then what will happen, your particle A become its antiparticle, B become its antiparticle, C become its antiparticle and D become its antiparticle. So after applying your charge conjugation operation, you will get a antiparticle of A interacting with the antiparticle of P leads to antiparticle of C and antiparticle of D. So from this one, what you understand, by applying the charge conjugation operation, okay, this operator changes the particle into its antiparticle without changing the direction of the particle and its spin. And the another thing is, this is conserved in strong and electromagnetic interaction, and it is not conserved in weak interaction. Let us take an example for the weak interaction. Like here you are applying charge conjugation operation on a beta decay process, okay, that is neutron decay to proton, electron and antineutrino of electron, okay. So here I just put R, okay. R is to represent a right handed screw, okay, of motion, okay, that we will come later on while you are studying the helicity, okay. And after applying this, you will get antiparticle of neutron, that is dk to antiparticle of proton, then positron, and the neutrino with a right handed screw, okay. So actually this is not going to happen or does not exist because all the neutrinos are left handed system, but you are getting a neutrino with a right handed system, because I already told the charge conjugation did not change the direction and its spin, okay. So these antineutrinos are right handed system, but neutrinos are not right handed system, neutrinos are left handed system, okay. So after applying this charge conjugation for this weak interaction, so you are getting a product that does not exist in nature. So you can say this charge conjugation is not conserved in the case of a weak interaction, okay. So the basic thing you always remember, your neutrinos, whatever may be neutrino of the electron or neutrino of the muon, they are left handed system, and antineutrino of electron and antineutrino of muon, they are right handed systems, okay. So that we have to remember. There are so many examples for showing the weak interactions are not conserved under charge conjugation, okay. So this is one example or beta decay process, okay. Now another important thing is the parity. The parity operation, it is represented by P cap, okay, and parity, you are applying parity operation on a state psi with components x, y and z. Then what will be your product? Product will be psi with a minus x, minus y and minus z, okay. So if you are looking at the Feynman diagram, this will be like this: A and B interacting, you are getting C and D. And after parity operation, what will happen? This is just reversed. B move to this place, C move to this place, A here and C, D here, okay. That means this is something like a mirror, okay. This is a parity mirror. Sometimes it is called a parity mirror. Now we will look, if you just apply one more time, what will happen? P square will lead to again psi of x, y, z, okay, and P square is equal to I, and eigenvalue you will get it as 1, and eigenvalue of P is plus or minus 1, okay. Or when a parity operator acts on an elementary particle state, we get eigenvalue plus or minus 1, okay. And eigenvalue plus 1 stands for even parity, and the eigenvalue minus 1 stands for odd parity, okay. Or in general, you can write operator P acting on the state psi, that will give you plus or minus psi, where this is the eigenvalues. And this parity is conserved in strong and electromagnetic interaction, and parity is not conserved in weak interaction. So here I am just giving some of the particles and its parity number. So for the cogs, parity number is +1, and for the anti-cogs it is -1. And for the baryons are made up of 3 cogs. So we have +1 whole cube, that is equal to +1. And the mesons are made up of cogs and anti-cogs. Okay, that is +1 and -1. So in mesons that will be equal to -1. And for the photons, the parity number is -1. So now the parity violation in beta decay was demonstrated by Wo's experiment. In this experiment they used cobalt 60, okay, and this is a unstable compound, unstable element, cobalt 60, and it decay to nickel 60 and electron and anti-neutrino, plus generally it has two photon as well. Okay, so now we are just looking at these 3 only. Okay, and if you do a parity operation, parity mirror, if you keep a parity mirror, so in this reaction, if you apply your parity mirror, what will happen is the direction of electron, okay, and the direction of magnetic moment, they are in the opposite, it should be in the opposite direction in order to for the conservation. Okay, so when you apply the parity mirror, then this will give you the direction of magnetic moment and the direction of the electron will be in the same. So this second case, this is not going to happen. Only you can observe all the beta decay in this manner only. Okay, so that is the observation by Wo's. And after the Wo's experiment, there are certain things we have to change. So before the Wo's experiment, parity is conserved in all interactions. Okay, but after Wo's experiment proved that parity is not conserved in weak interaction. Second things, all interactions are invariant with respect to reflection. Okay, but after Wo's experiment, what we understood, weak interactions are not invariant with respect to reflection. The third thing, any process looks plausible when viewed in a mirror, but after Wo's experiment, the mirror image of a weak interaction might describe an impossible process. And the fourth thing is, before Wo's experiment, nature does not differentiate between left and right, and after Wo's experiment, what we understand, nature does distinguish between left and right. Another example of parity violation is you have another decay process and is converted to proton, electron and antineutrino, electron antineutrino, and this is with a right hand system. Okay, now after applying the parity operation, what you are getting is neutron, because proton, electron and antineutrino with a left handed system. Okay, so that is the parity operation changes an antineutrino that moves in right handed screw motion to a one which moves in a left handed screw motion, and such a thing does not exist in the nature. അപ്പോൾ അത് പറയാൻ കാരണം നേരത്തെ നമ്മൾ ഓൾറെഡി പറഞ്ഞതാണ്, എല്ലാ ന്യൂട്രിനോസും ലെഫ്റ്റ് ഹാൻഡഡ് സിസ്റ്റമാണ്, അതുപോലെ തന്നെ എല്ലാ ആൻറ്റി ന്യൂട്രിനോയും റൈറ്റ് ഹാൻഡഡ് സിസ്റ്റമാണ്. അപ്പോൾ നമ്മളിവിടെ പറഞ്ഞിരിക്കുന്ന ഈ ഒരു പാരിറ്റി ഓപ്പറേഷൻ്റെ ഔട്ട്പുട്ട് എന്ന് പറയുന്നത് ആൻറ്റി ന്യൂട്രിനോ വിത്ത് ലെഫ്റ്റ് ഹാൻഡഡ് സിസ്റ്റം, അങ്ങനത്തെ ഒരു പാർട്ടിക്കിൾ എക്സിസ്റ്റ് ചെയ്യുന്നില്ല. സോ ദിസ് ഈസ് എ ക്ലിയർ വയലേഷൻ ആൻഡ് the parity operation is not conserved. Okay, now if you apply both the charge conjugation and parity together, then what will happen for the same interaction? So for the same decay process, so here you are getting antiparticle of neutron, antiparticle of proton, then positron and a neutrino with left handed. So that is existing. okay, and all the neutrinos are left-handed system. Okay, so that is Cp is almost always conserved. Okay, some cases like KL0, KS0, dk 2 pi on violate the Cp conservation. Now we will go to the TCP theorem, that is, if we apply all the three operations, time reversal, charge conjugation and parity, in any order, whatever may be the order, on any equation depicting any reaction between particles, we obtain a reaction which is also possible. Okay, that means ഇതിൽ ടിയും സിയും പിയും നിങ്ങളൊരു ഇൻട്രാക്ഷൻ്റെ അകത്ത് അപ്ലൈ ചെയ്ത് കഴിഞ്ഞാൽ അത് കിട്ടുന്ന ഔട്ട്പുട്ടും അതും പോസിബിൾ ആയിട്ടുള്ള ഇൻട്രാക്ഷൻ ആയിരിക്കും. ഓർ യു ക്യാൻ സേ ഓൾ ഇൻട്രാക്ഷൻസ്, ദാറ്റ് ഈസ് സ്ട്രോങ് ഇൻട്രാക്ഷൻ, ഇലക്ട്രോമാഗ്നറ്റിക് ഇൻട്രാക്ഷൻസ് ആർ invariant with respect to the combined operation of TCP, and this is called TCP theorem.